Today we're going to take a look at monopole antennas. Okay, so monopole antenna is basically just an antenna with a single conductor like a pole. So all of these antennas here are monopole antennas except for this one. So I just wanted to show you that just because it looks like a monopole antenna doesn't mean it is. So this one is actually a dipole antenna. So we have our monopole here and then the other half coming back down over the shield there. So for a monopole antenna, the most common length is a quarter wavelength. To calculate the wavelength, we use the equation lambda equals v over f, where lambda is the wavelength, v is the speed of light in a vacuum, and f is the frequency. V is equal to 300,000 kilometers per second, or 300 million meters per second. So lambda equals 300 million meters per second, all over 5.8 billion cycles per second. So let's just take the units down and see how they cancel out, and we're left with meters. So lambda equals 51.7 millimeters, or 2.035 inches. So quarter wavelength would be 12.9 millimeters, or 0.509 inches. When designing a quarter wavelength monopole antenna, it's a good idea to just start out with a longer conductor than you need and then trim it down to tune it to frequency. Now let's take a look at these two quarter wavelength monopole antennas that I trimmed down for the best SWR. So taking a look at the graph, we can see that the antenna has an SWR of about 1.33, and taking a look at the Smith chart, we can see that everything across the center line here is a resonant frequency of the antenna. Everything in the top has a net inductive reactance, and everything in the bottom has a net capacitive reactance. So now let's look at this other antenna. So you can see it also has a pretty good SWR of 1.4. It's under 2, which is good. Look at the Smith chart and it looks a little different. So we took two antennas that had to be trimmed to different lengths in order to match them as best as possible to a 50 ohm impedance. This is a good example of how the transmission line can affect the performance of your antenna. Pretty much everything near your antenna can affect the impedance and degrade the performance, so it's a good idea to do the final tuning of your antenna in the environment that it will be used in. Here you'll see that this clear vinyl tubing negatively affects the performance of this antenna by increasing its SWR from 1.3 to about 2.7. Antenna designers take this into account and tune the antenna inside the enclosure it will be used in, like this dipole you saw earlier. So you can see that the SWR is about 1.1 and it's about dead center on the Smith chart. So if we take this protective enclosure off the dipole antenna, you'll see that it changes the SWR from about 1.1 to about 1.5. Now it's still pretty good either way, but you can tell that the designer had the enclosure in mind when tuning it. So now the question, why quarter wavelength and not whole wavelength? And I'll show you. So we take this copper wire and we cut it to one wavelength. Actually it's cut a little longer so that exactly one wavelength is sticking out of the center conductor of the connector. So you can see that the SWR is about 3.6, even though it's a resonant antenna. So you could use this antenna, but you'd have to use a balun to match the impedances from 14 ohms of the antenna to 50 ohm transmitter. Another parameter that changes when going beyond quarter wavelength for a monopole antenna is that the radiation pattern changes. Quarter wavelength vertical monopole antenna mounted above a good ground plane gives us a nice uniform omnidirectional radiation pattern like this. When we go above a quarter wavelength, the radiation pattern becomes less and less omnidirectional. For your application, this may be fine because the benefit of a longer antenna is that it has more area for reception and can transmit and receive above surrounding objects. Many monopole antennas that are mounted on cars are about 5/8 of a wavelength long for this very reason. Just like the impedance, the radiation pattern of an antenna is pretty much affected by everything that's nearby. In the last video I said that an antenna system is a complex RLC network. The resistance is composed of R loss and the radiation resistance of the antenna elements. R loss is from the actual resistance of the conductors, and power dissipated in this manner is lost as heat. This value is not stable like in a DC circuit and varies with frequency, so you can't measure this with a multimeter. The impedance is in ohms and is composed of the total resistance plus the inductive reactance subtracted by the capacitive reactance. Remember that the antenna is said to be resonant when the inductive reactance and the capacitive reactance cancel each other out. Now, an antenna does not need to be resonant in order to be a good antenna, and it's not always practical either. For example, a quarter wavelength monopole antenna for a 60 kHz transmitter would be well over a kilometer long. In the next video, we'll discuss dipole antennas and go into what the gain of an antenna is and how it's measured. See you next time.